Yeah, so let's start. So today we'll discuss about OpenMP and MPI. So OpenMP is actually auto threading model, a thread pooling model. So it is implicit threading. So automatically it gets threaded, and it is shared memory model. And today we'll discuss about distributed programming model and what is the benefit of distributed programming model. Also we'll discuss. This thing already we have seen these things. So I am quickly going through this thing. Okay. So OpenMP is compiler directive and automatic parallelization should do, and it auto generates threaded code and gets synchronized. So we don't need to do, and it is very simple. In the last class, means day before yesterday classes we discussed. So using simple compiler options, this is compiler directive, pragma OMP parallel and pragma OMP parallel for schedule. So this is a compiler directive we provide in the code, and compiler generate the threaded code automatically, and static time code, and at runtime you can provide number of threads. Okay, so gcc minus app openmp test.cp do, and then export omp num threads is equal to 4. This is actually at runtime we are giving the how many threads you are going to run, and this is actually whenever it compiler generates, it's assume uh, number of thread to be a variables, and that variable gets set during runtime. Okay, so from the environment variables, and automatically it suppose OMP number of thread is equal to 4 means this for loop will run with 4 thread. This is sequential code, and that some sequential code can be, this is manual parallel. So suppose ID is equal to num get thread numbers. This gives actually thread number, and this is actually total number of thread. OMP get num threads. Okay, this is thread num and this is num thread. So this is thread num is a thread ID, and it is total number of threads. And if you have this information, then you can divide the data distribution among threads. Okay, so this is actually manually distributing the data. So manually distributing means you will get to know what it is happening. And in previous case, we don't know how it happens, but whenever you say OMP for parallel static means it will create 4 threads, and it will divide the, what I can say, iterations into 4 part. So, and each part will give to 1 thread. This is auto parallel one, so same thing. And work sharing for parallel loop. So if you look at this is pragma OMP parallel. So this is for 1 to 13, and this is for 3 threads. Suppose you are doing, then it will pragma OMP parallel means, and pragma OMP per, it will fork, or it will create 3 threads, extra threads, and it will assign work. And after that, it will put implicit barrier. So these are implicit forking and implicit barrier. So we don't need to write the fork, but automatically it will do. And thread are assigned to an independent set of iterations, and thread must wait at the end of the work sharing construct. This is a work per thread. And threads are assigned an independent set of iterations. So 1, 2, 3, 4 independent in this case, 5, 6, 7 are independent sets, 9, 10, 11, 12 are independent sets. Independent iterations get assigned. And in a program, we can have actually not one, what I can say, parallel sections, may have multiple parallel sections. Okay. So in this case, what we are doing actually 2 parallel sections we are seeing. So pragma OMP parallel for and pragma OMP parallel for, there are 2 parallel sections are there. Okay. So one parallel sections for n is equal to 1000, and other is m is equal to 500. One work for one set of array, and another parallel for work for another set of arrays. Okay, in this way, this is a serial part. This is a printf, and this is serial execute, and this loop will get executed parallelly. Okay, and here this second loop also get executed parallelly. Main thread is executed, and along with parallel worker thread will execute. And we have covered up to this point. So in the last class. So next, what we can do, what extra we can do. So we can do critical construct also. In OMP, we have a concept of a private LSUM. So we can do pragma OMP parallel. So in this case, suppose you want to calculate sum of n numbers. Okay, you can do local sum locally. So pragma OMP for we are doing for I is equal to 0, I less than n, I plus plus, and this is actually for each thread it is doing. And after that, pragma OMP critical. This thing we are doing for summations. Okay, so this L sum is local one and sum is actually global one, and sum is equal to sum plus local sum we are doing. So here in this case, clearly what we are writing. So this is the, let me change to pointer. I think this don't have actually ledger pointer. It's fine, but this is a pen. Okay. Okay, so we don't require pen, maybe. So this part, particularly in this case, pragma OMP parallel private, this L sum is actually private variables. Okay, private variable per each thread. Okay, so whenever you are creating, and this L sum is getting calculated for each thread. Okay, and after that, pragma OMP critical. Here for all threads. Okay, so summation is the critical one, and this L sum value get added. So in this way, we can write actually shared variable one also. So in this case, L sum is private and sum is critical one. And thread waits for their turn, only one thread at a time in this case. So OMP critical it. And whole block, pragma OMP parallel, private L sum. This is the whole block. Okay, so starting from curly braces to end, curly braces end. So in C or C++ code or Java code, we see a block of code means it is started with curly braces. And same thing can be do with actually reduction clause. Okay, so this is a reduction clause. So we are reducing or addition of all variables and summing to some variables. So this is the earlier things. This same thing can be rewritten it with reduction clause also. Sum is equal to 0, then pragma OMP parallel for then reductions we are doing, and what operations for reductions we are doing, plus operations, and final variable is a summation variable. This is sum is the shared variables. And if you do this thing, then what automatically it will generate the previous code. Okay, so if you do OMP parallel for reductions and sum is shared variables, then it will generate the, it will divide the this for 0 to n into suppose 4 threads rather than 4 pieces with some local variables, local L sum variables, and after that sum will be final calculate sum will be done with shared variables. So if you do for reductions, then it will generate internally this kind of code automatically.
Sir, in
Yeah.
the for reduction, if we did multiply and then sum, then all the local sums would have been multiplied.
Yeah. So in this case, these operations, in this case, we are doing some operations. For this thing, you need to match. So if we are doing some operations, okay. So reductions will be for this reductions will be for what you can say summation operations. So this code will actually parallel OMP for this will be sum is equal to sum plus L sum it will do. But if you write here suppose multiplications, then it will do local summations and then whenever it's changed to final one, so in this case it will replace star.
Okay, sir, got it.
So that is not good idea. So same things you will. If you are averaging sum, then here also you use same sum. If you are using multiplication, you use same symbol there also. Okay, so it will do the same operations better. And reduction means a summation of all things or multiplication of some things. Any operator. Okay. Reductions means summation of all or multiplication of all or some operation of all. We do no. Reductions mean. And standard reductions is have you do you know what is map reduce? So in the first class I have explained what is map reduce. So map reduce is that is standard technique. So let me look at pen. So map reduce, what is map reduce? Map reduce is uh, suppose summation of what we're trying to do, summation of suppose xi square we are doing. So s is equal to summation of xi square. Then what we are doing? Suppose xi for this case, so x1 square plus x2 square plus then xn square we are doing. So in this case, this is actually mapping. So for every x we are mapping. So x is mapped to x square, okay, or x into x. Then every element x is mapped to x square. Then summing up all the x square. So this mapping of x to x square is map, and then summation of all x square is reductions. So whenever you say map and reduce, then map reduce have two formats. So two functions. One is map functions. It will do the mapping functions for all element, and then reduction means it will do one common operations and reflect to a final. Uh, in this case, final sum. If it is multiplication, then final multiplications. Okay, final result of multiplications or any operations. Okay, so this operations in this case it is plus, but in any kind of operations can be done.
Excuse me, sir.
Yeah.
Sir, here we can, without using make reduce, you can use, we can parallelize this directly also, right? We can just, first of all, parallelize the squaring operation and then we use private reduction for adding them like we did in the last slide.
Yeah. That we can do. But if it's means OpenMP gives of some way of doing, then why not to use directly?
Okay, so it's basically syntactically better, right? There is no other difference, right? Okay.
Okay, so and OpenMP have another most important thing, that is scheduling. So by default, if you don't write anything, schedule. So in this case, if you look at previous case, if you look at pragma OMP parallel for, then by default it will do a static scheduling and divide the whole iterations into by number of threads. Suppose n is equal to 1000 and number of thread is equal to 4. Then it will divide 250, 250, 250, 250. So, and 250 will give to first thread, then second thread, third thread, fourth thread. And so it will do static scheduling, divide n by number of threads. So this is standard it will do. You can change that scheduling. So we can do schedule, then type and chunk. Okay. So there are two kind of schedule. So one is static schedule. So iterations divided into chunk if specified, or and statically assigned to threads. And dynamic one is iteration divided into chunk and if specified and dynamically schedule among threads. So what is the difference between static and dynamic? Let me give you some examples, then it will be more clear. Okay. So let's look at the static scheduling. So if you are not giving any informations, simply parallel for them, by default it will do the static scheduling. So most compilers split the loop into, if you look at this thing, n by p, n is number of iterations, p is number of threads, then n by p chunk by default. This is called static schedule with chunk size n by p. So for example, there are, suppose you have a loop with 100,000 iterations and 4 MP threads. The loop is divided into as follows: thread 0, thread 1, thread 2, thread 3, and 0 to 250, then 250 to 500, 500 to 750, and 750 to 1000. This is the standard. Okay, if you are not doing any scheduling, by default it will do static schedule. If you specify, so pragma OMP parallel for, then what are schedulings? Schedule, static, and chunk size is 10. So here, suppose Sam 1000 iterations and 4 OMP threads and chunk size is 10. So then what it will do, 1000 iterations, it will divide the 1000 iterations of chunk of 10, 10, 10. And it will assign means round robinly. So this is if you can see green, red, purple, and is light blue. Okay, so this is green, red, purple and blue. So these things are threads, and this get 0 to 10, 10 to 20, 20 to 30, 30 to 40, and then it repeats. Okay, so the green one is thread 01, then red one is thread 1, then purple one is thread 2, and this blue one is thread 3. So in that way it will assign. So this, it will divide the whole 1000 iteration into 10 chunk of 10, 10, and it assigns statically round robinly. Okay, and it's statically assigned. Is this clear?
Okay, sir. And sir, when we discussed about the reduction, we say that the sum would be a shared variable, like in the heading. Hello? Hello?
So yeah. So in that case, it will deal differently. Okay.
Hello?
So please ask your questions. Hello, am I audible?
Hello?
Yeah, please tell. Somehow means he's not audible. Let's we can take his questions offline maybe. So issue with static schedule. So while static scheduling, the number of iterations is evenly distributed among all the OMP threads. Even every thread will be assigned similar number of iterations. So this is not always the best way to partitions. So why? This is another example. So in this example, what we are trying to do. So AI is equal to square root of BI plus CI, and square root timing is data dependent. So and this may cause actually load imbalance. In this case, 2, 3, 4 will be waiting for uh, long for thread 1 to finish. So suppose this is static schedule, and in this case, suppose thread 1 takes a little bit longer time, and other threads, particularly 2, 3, 4 threads, other threads takes actually less amount of time. Suppose, then what will happen? Then for this thread to finish, other thread need to wait, because finally we need to do a common barrier. So for creation of thread, and that will be a common barrier. So that's why when static scheduling may not good when this per iterations the work is not balanced. Is this clear? Hello?
Yes, sir.
Excuse me, sir.
Yeah.
Sir, in static scheduling, when is it better to actually manually provide like how many like what size of each this iteration is split into, rather than the operating system itself dividing it into n by p threads, like according to the number of threads?
No, manually dividing also. So if you know, means if you profile and know that for each iterations, what will be the time if you know, then manually dividing is very good.
I did not get you, sir. Can you repeat?
So if you profile the code for each iterations, how much time it is taking, and for all iterations, its number of time is actually same, then manually doing and doing statically is better.
Oh, okay, I got it. Okay. Thank you.
So in this code, so are you able to see this code? AI is equal to square root of BI plus CI. Square root, it is not fixed for all the values. This timing it takes is depend upon different data. It is data dependent one. Similar kind of many such operations we were doing, where for each iterations the timing is not fixed. So in previous code, so in this simple code, for every iteration it will take same amount of time. But for this kind of code, for data dependent one, so we should not do static schedule. So if you do dynamic schedule, then it will be much better. So in this case, we will have actually a dynamic schedule. With a dynamic schedule, with new chunks are assigned to the threads when they come available. When they come available, first assign 2, 3, then it finishes, then go for next assignments. Are you getting my point? So loop iterations are divided into piece of size, And when a thread finishes one chunk, it will dynamically get the next chunk. It will get chunk dynamically. Another thing is schedule guided, similar to dynamic, but chunk size is relative to the number of iterations left. Okay, and although dynamic scheduling might be preferred choice to prevent loaded wells, in some systems there are significant overhead involved as compared to the static scheduling. So static scheduling is much more simpler. But if you know that your operations per iteration is very over different iterations, then it's better to go for dynamic scheduling. Is this clear? So this is the way, means suppose there are these examples. So in this case, so AI is equal to BI into CI. So in this case, what we are doing? We are doing some suppose operations, some operations. So not plus operations and some operations. So this operations is let's see. So this is not plus operations. We are doing some other operations. Okay. So this operation is some operations. AI is equal to, so suppose BI and some operations we are doing, OP. And these operations is not same for all data. So it is data dependent operations, suppose you are doing. Independent operations, but data dependent operations you are doing. Then in this case, so static schedule may not give better result. So go for dynamic schedule. Maybe you can say means chunk size may be different. So in this case, static you make it dynamic. And chunk size you can make 10. So if you make dynamic schedule, then so first it will assign first these iterations, first set, it will initially assign. Okay, then when a thread finishes, then only it will assign the next guys. So this color may change in dynamic case. So if suppose this guy finish first, then this will be assigned to this guy based on how quickly it finishes. Dynamically it balances the role. So whoever finish first, it will get another chunk. Number of chunk will be finished by different thread will be different for dynamic scheduling. Is this clear? If no question, then hope it get clear. Okay, and there are more examples of OpenMP as they're available. So these are two links I am providing, and a lot of examples, around 10 to 15 examples are there. Okay, so particularly second link, it provides a lot of examples. Okay, next we'll move towards actually HPC. So this MP programming. So if you look at OpenMP, Silk we have not discussed, but we'll discuss maybe later. So pthread programming, these are actually all shared memory programming model. So within the same process, it will do. Okay, so it will create thread and do. But whenever we are going for shared memory programming model, so it is limited to one machine only. So whatever you do, it is limited to only one machine. So one PC. But if you want to go for multiple machines high-performance computing, then this threading and OpenMP will not work. So anyhow, we need to go for higher level things, distributed memory programming model. So modern HPC system, almost high-performance computing, our Paramation or our bigger cluster, all are multiple node or multiple computer, multiple blade systems, and we cannot go for only shared memory programming model, because shared memory programming model or pthread programming model or OpenMP programming model, so these are all limited to only one machines, one node or one computer or one blade. So if you want to utilize multiple node or multiple computer or multiple blade, then we need to go for different programming model, distributed programming model. Okay, that is MPI programming model. And solving large problems, particularly scientific simulations, computational, then CFD, data analytics, we require one machine is not sufficient. That's why we go for high performance computing. And for that, the programming model is distributed memory programming model. And we use MPI, message passing interface. And there are 2-3 standard MPI models are there. And it can be used for large scale programming. Okay, so have you heard about MPI programming? Hello, students.
Sir, is it message passing?
Message passing interface. MPI means message passing interface. So
Okay.
pthread, OpenMP, vectorize, these are all means shared memory programming model. So within one PC or one laptop, one node can be utilized. But whenever we're utilizing multiple machines, then we need to go for distributed memory programming model, and particularly MPI is the good one. We can go for large scale programming. And HPC courses, if you are not discussing about MPI programming, then it will not make sense. So even if our course is not intended to do any programming, but we should discuss MPI programming model. So writing parallel program using MPI. So this is basic funda. Suppose you want to write a very big program. We want to solve a very big problem. And in general, suppose big problem is it takes huge amount of time to solve in a single machine. Then in general, we want to run in parallel machines or multiple machines. Then definitely, so what question arises? So what are the solutions and what is the algorithm we'll use? And design solution with parallel algorithmic technique. So this course we are not going to read about parallel algorithm. Okay, so this is for high performance computing system and just analyzing, but not the parallel algorithm course. This is not, scope is not for this course. So if you want parallel algorithm course, then there is a separate course. But we'll discuss about the MPI, then means interconnection architecture, and then general settling. Okay, not the parallelisms. Okay, or parallel algorithmic technique, but lower level resource management we looked at. And whenever we looked at very big problem, so we generally try to solve using parallel algorithmic technique, and general to solve a data intensive one or function intensive one, then we try to divide the things into pieces. Okay, so bigger program into smaller pieces. Okay, so this is the general standard methodology. So generic parallel algorithm design is poster methodology. So this is very high level one. So we have only one slide for this. So first thing is partitioning. So process of dividing the computations and data into pieces. So both computations and data you divide into pieces. So a good partitioning split both data and computations into pieces. And the standard terms people use is domain decompositions. So divide the data into pieces and associate computations with data. So in our earlier case, so domain decomposition we did. So we have actually 1000 iterations and 1000 datas. Okay, A is equal to BI plus CI we are doing. So for each iterations, there is data points, and we divide it into 4 separate piece of data. Separate piece of data means 0 to 250, 250 to 500, 500 to 750, and 750 to 1000. So we divide into 4 domains. So, and we associate computations with 4 domains. Okay, so this is domain decompositions. Then communications. Identify the communications pattern between the partitions and interpartitions. Suppose you partition in means this data, or you partition the computations into multiple domains. Then between the domain, so how much communications you require? Identify the communication pattern between partitions and interpartitions. Then after that, agglomerations. Agglomerations is combining process of grouping partitions or tasks into larger tasks to reduce communications. So once you do that thing, then you assign the tasks to processor. So agglomerations is actually partitioning means suppose. So in this case, first case, suppose we have 1000 iterations. I am giving very simplistic example. So earlier case example. So in a for loop, we have 1000 iterations and we have 4 processor. So naturally we'll think you have 4 processor. Why to divide this 1000 iteration into means 1000 smaller tasks, smaller work? It's better to divide into 254 bigger work. So that will be better. So instead of dividing the whole 1000 into means one individual one work, we divide into 250 works. So that we'll have actually only 4 bigger work and 4 work assigned to 4 different processes. So this is very easy. Okay, so if you divide into very smaller work, suppose each individual iteration say make it work, then what will happen? So every individual works after doing that thing, you need to start the things, okay, start the parking and barrier, then again reassign. So automatically it takes more time. It spend more time in communications. If you do the agglomerations, but that means if you mix more smaller number of taxes and create a bigger taxes and then assign to the process, then it will be better. Okay, so earlier case it was whatever I've seen is very simpler for loop, but this can be applied to a bigger taxes also. Okay, bigger taxes. So suppose a very big competitions. Have you heard about any scientific benchmark? So Montage, LIGO, SFT. So there are many bigger workflow, we say workflow. So where you require huge amount of competitions. So have you heard about sky mosaicing? Our sky. So if you look at our sky, so some to analyze the universe, so to take photograph of whole sky, so people take actually thousands, means millions of very high intent, means what I can say resolutions image, and they try to merge all the image to create a very large image to analyze clearly. So in that case, huge amount of data, huge amount of computations need to be required, and that need to be performed in a very big machine. Then only you can do. So that process, in general, they make in a workflow, and initial data comes from all the sensor, all the cameras, and then they combine, and then they mix and they create a final mosaic. So there is a clear-cut 5 or 6 different process, page-wise it too, and it is a kind of DAG or graph formats. So this competitions may not be in simple for loop. It may be in a bigger DAG format or graph format. And some algorithms also applies. So for this kind of work, so for detail, so there is a very good book in parallel algorithms. Okay, so Bipin Kumar, University of Minnesota, they do a very good work. They did very good work in research, particularly graph merging, graph agglomerations. Okay, so the very good work how bigger graph can be merged into smaller graphs, means combined into small ones. Many taxes combines and communication get reduced, and overall number of partition get also reduced. Okay, so that is called graph specifications. So we will not go detail about this Foster methodology in detail. So this is the only one slide we are putting, and now we'll focus on message passing interface (MPI). So message passing model. So this is actually a process, is a program with a PC and address space, and process map multiple threads and with sharing single address space. And MPI is a communication among process which have separate address space. Okay, and inter-process communication consists of synchronizations, movement of data from one process to another process space of another process. Okay, so this MPI program can be run on single machines. Also, it can run on multiple machines. Okay, MPI program, message passing model, can be run on single machines. Also, can be run on multiple machines. And how to install MPI on Linux machines? So this is very simple. So either you, if you are using a sudo apt-get install MPI ch2 or MPI ch2 or OpenMP in Ubuntu or Fedora, you just install OpenMPI or MPI ch. It will install on your personal machines. and you can easily write program. So suppose hello world program mpicc and running mpi run minus np4. This one is actually on 4 process we are running your mpi program, and whenever you do, 4 copy of hello.mpi process will run. So this is very once SAM hello_mpi will run, but 4 separate process will run, and they will collaboratively work. So based on what work you have provided in your hello_mpi. So if you want to see very small demo, maybe I can give you very simple examples. So just connect, otherwise I connect. Yeah, connected. So are you able to see my screen? Hello?
Yes, sir.
Very simple example I am giving. So mpi hello.c. So this is very simple code. This is hello world program only. But even in hello world, we have actually many things: mpi init, mpi com size, mpi com rank, and then mpi finalize. Every program have actually, this is the bare minimum code we have. 1, 2, 3, 4, 5, 6 line bare minimum code, just like stdio.h kind of thing. Then after that, in this case, we're running the hello world program. Okay, so compilation is mpicc. So what we are trying to do, this is compilations, and then if you run the a.out, then by default it will run on single processor. Okay, so single process. But whenever you run with mpi run, this is mpi run, it create environment. Then what are putting number of process on how many number of process we want to run. Suppose I am putting instead of np is equal to 10 and ./a.out. Then what it will run? It will run 10 copy of 10 process of a.out. So it will run 10 copies of a.out. So you can see we are running 10 copies, and for one copy it is saying number of MBA tags is 10 for master, and other cases it is hello from tax 1, tax 0, tax 2, tax 3, and other things we are doing. So if you look at the code, so what we are trying to do, if tax ID is master, I mean we have defined master is equal to 0, then only print this thing. Okay. Otherwise, for other taxes, for all the taxes, you print tax ID and host name. So this is very simplistic thing, and these are all different process. Okay, so whenever you run mp run minus mp10 means it create 10 different process. It's not like that OpenMP and pthread for one process of many threads. It creates actually many processes. An MPI program can run on not only on one machines, but it can run on multiple machines. Okay, suppose you configure MPI installations on multiple machines, then one can run MPI program on as many number of machines, and it uses NFS, NIS, and network concepts, MPI send and MPI receipt, written in terms of actually network. So process of different machines, it go and create process and they communicates through enterprises communication through network. So in that way, MPI is more flexible to write program for high performance computing system. It is clear, and MPI is yeah. Hotend program also one can write. C program, yeah.
Sir, in this case, the example which you just showed, like all the 10 processes will run the exact same code.
Same machine, same code on the same machines in this case.
Okay.
But if you configure the MPI program on a big machines, many set of machines, then whenever you run, it's run on different machines, but the same code runs. For all the process, the code is same because it created many process. Okay, as it created many process, so for different process, the address space is different. And because we are running on top of MPI run, so every process get one MPI rank. Okay, MPI rank or process rank or ID. And based on ID, what part it will execute, it will decide. Okay, so if you look at the earlier code, so let me show the code. So in this case, if tax ID is master, then only it will execute this part of code. If tax ID is not master, then it will execute other code. Suppose if I say tax ID is 6, then it will execute some other part of code. Then that also can be done. Okay. Suppose what I do. So what I'm trying to do, if tax ID is 6, suppose tax ID is 6, then only something if tax ID is 6, then only 6 taxes only executes. So what you are trying? So if you look at, so for tax ID 6, so for tax ID 6, it executed a separate thing. For master, it executed separate thing. For rest of the things, again, it executed the same thing. Okay, so everyone will run the same code. Okay, everyone will run the same code, but based on the tax ID specific area, so it will run the specific code. So in the code itself, you can write if it is process ID 0, then what will be executed? Process ID 1, what will execute? Process ID 3, what will execute? You can define, or you can create master or slave kind of things. If master is there, then what it will execute and what other people executes. And that way you can divide the work. And if they want to communicate, they need to communicate because this is not shared memory model. This is not shared memory model. So suppose you declare an array, then that array will be for that process, not for other process. Other process will not be able to see unless you are sending the array address and sending the data. So that's why in MPI, so in general, it is a separate process. Okay. And if they want to communicate, they need to communicate through the network, or if it is same process, inter-process communications. Suppose same process means same machines. So we don't need to go through network, but it will through inter-process communications. And a program is a performing task on a processor. Each processor or process is a message passing program, run an instance or copy of program, and written in conventional sequential language C or Fortran. Okay, so typically single program operating on multiple data sets, and the variable of each subprogram have the same name, but different locations, different distributed memory, and these are different data. All variables are local to the process. We have created 10 process. Okay, suppose you declare in the code array AI, array A10, then array A10 will belongs to that process, not to the other process. Okay, because you are creating 10 separate process. Array AI of process 0 will belongs to each area. All variables are local to the process and communicate by a special message passing that is called send and receive. And every process of MPI different. Okay, so in this case, kind of things, this program data. If this is the one process, another process, suppose you have created 10 process, then every process have their own data. This is not shared memory, it is distributed memory programming model. And in general, every process of MPI different. Suppose hi, single persons you do touch your nose by left hand. Hi, touch your head by right hand. This kind of thing. And another thing is hi, all person do all the jobs. Touch your nose. Kind of things. Well, separately you can write based on your command and all the things. And every process of MPI difference. How to do work collaboratively. MPI program, some example. Suppose assume 10 persons who want to do sum of n numbers. So first person, what it will do? Manager is responsible for IO. So get input from keyboard, send data to each persons. Okay, send one data to each persons and get sum from the second person is other persons, and display the sum. And what other persons will do? Every person have some rank or ID. Okay, every other persons, because every process is different. Every process have some rank or ID number. Receive data from master. Receive a sum from rank 1, rank plus 1 means the next guy. Okay. If I is less than equal to 10, if rank is equal to 10, sum is equal to number, else sum is equal to sum plus number. So next guy, everyone is sending, and send the number to the rank minus 1 persons. Okay. So previous guys. After summation, it's sent to the previous guys. So this is one model. Another model is suppose master sending data to means all means suppose 10 persons, assume 10 persons, 11 persons. Suppose 100 data need to be summed. 100 data need to be summed, and there are 10 persons. This and one master is there, so total 11 persons. So master will get this 100 data, send this 10 data to each persons. Okay, they will do the summation, local sum, and master will collect the local sum, and he will get the he will accumulate the final sum and then display the final sum. That is also another way of doing. Okay, so somehow, so we need to collaboratively do the work, and because here data space is different, we need to send the what I can say data through send and receive message. This is very high level MPI program it is doing. So this is a if rank is master, get input from keyboard, send one data to each person's. Okay, scatter. So get sum from second person. Sum is equal to number plus summations. This is actually from master, and after getting all the summations, then display summations. So this is we are getting from the only second person. First persons who are sending data to all people, then getting summation from the second persons. Okay, I'm the first person, master is the first person, second person who are getting the thing. And S is equal to num plus sum. Initially sum is equal to 0. And what other people are doing? So if I less than receive a sum from rank plus 1 persons. Okay, first thing is receive data from master. So first thing is this send we have done. First it will receive, and then if I less than or equal to 10, then receive a sum from other pluses. If rank is equal to n, then sum is equal to whatever I have received. Else sum is equal to sum plus d. Because first I will receive, then only I will do sum, and then send the sum to my left guy. Okay, so rank minus 1 guy. So first all the number will get distributed to all the people. Then summation will come from right side to left side, 10, 9, 8. Then it comes to 1 and 0. And at 0, sum will be calculated. And this way, collaboratively, we can do MP program. So ultimately, what do we have? We have send and receive functions. And for master, the code executions will be different. For other, the code execution will be different. But you can create multiple master, multiple collaboratively, how you can do that, you can do. So now time is up, I think so. If you have any doubt, you can ask. So we'll have actually many examples program. Okay, so next class. So we'll have 2-3 examples so that it will be more clear. If you have any doubt,
Sir, like I was asking about private variable and shared variable. So if we did not mention any variable as let's say private, then everything is considered shared.
no, no, here everything is considered as private.
No, in OpenMP.
So OpenMP by default it is shared.
Okay.
It is shared memory programming model. That is all in one process. OpenMP is everything, it is in the one process. One process means just like multi-threaded programming model. So most of the things are shared. So except their stack space and thread specific data, most of the things are shared. So that is shared memory programming model. But in MP, all processes are separate. So we cannot declare as shared variables here. Because all will execute on different machine itself, not in the same, not even the same PC maybe. And they will communicate through network. Any other questions? So next class we have 2-3 examples. Okay, so we'll see 2-3 examples and we'll get to know many things about MPI program. Okay, thank you.
Thank you, sir.